All right, our last talk will be given by Rajaraman, who will speak on competitive data structure dynamization.
Thank you very much, Kirk, and thank you very much to the organizers. Okay, I guess I'm the last talk between us and a long walk that some of us will be doing. So this work is on competitive data structure dynamization. This is joint with Claire Matthew, Neil Young, and Arman Yousefi. And this is a couple of years old, but we have made some progress since the original SODA paper, but I'll mostly be very high level. And so this work started off, just to give you some background, this started off some work that Arman at Google was working on with the Google Big Table. And Neil sort of led the project, and we got involved in it. So it is a combination of an external memory data management problem, and where my interest more come in is in the context of online algorithms. So hopefully you'll get a high-level sense of what's going on and a bunch of open problems in this space. Okay. Thanks to Neil Young for the slides. The slides are excellent, but all the mistakes are mine because I tried to make some changes to it. So, okay, so I'm going to start with a very simple setting. It's a very, very simple online set covering problem. Not the traditional online set cover, but here is the situation. You have an online sequence of n items, only insertions. N items are coming over time. And your job is at some point to maintain a set cover over these items. Okay, so you just have to maintain some sets over these items. There are two costs that you have to worry about. One cost is on, let me try to use this. So one cost is the cost of building a set. And when you try to build a set, the cost you pay is the total number of elements in the set. The other cost you have to keep track of is how many sets you're maintaining in your cover. Because at all times, you're going to pay a total cost, which is the sum over all times of the number of sets you're maintaining in your cover. Okay? So let's consider a very simple instance. Consider your, at every point of time, you introduce a new set. Yes?
How are the sets specified? Are they kind of, as you get elements, you say for each set, is this element in it? So like you're looking at the instance matrix and you get it one column at a time?
So you design the sets. So as soon as an element comes in, you decide whether you're going to create a new set or you're going to place it in one of the sets that already exists. Okay? And these two examples will make it very clear. Okay? Okay, so this is a very, very simple algorithm which basically optimizes the first cost. As soon as an element comes in, it builds the set. Okay? So when element 1 comes, you build set 1. 2 comes, you build set 2, set 3, set 4, set 5. The total cost for an instance of length n is theta n square. Okay, people see that? And why is it theta n square? Well, the build cost is very small. The build cost is only n because it's 1 plus 1 plus 1 plus 1. But the second cost, which we will soon call it, is the query cost, is theta n square, because if initially it's 1, then it is 2, then it is 3, then 4, and then 5. Okay? A second algorithm, opposite to divide, is unite, which is whenever something comes in, you put it all in the same set. Okay? If you do this, so for this instance, you will basically just maintain a single set at the very end. So the second cost is just linear, because there are only n steps, and in each step you're paying a cost of 1. But it's the first cost that you're rebuilding again and again, and you pay a theta n square. Okay? Okay, quiz. What do you think is the best thing to do in this situation? Okay, so this is not even a problem. It's just one puzzle. So it's just a sequence of n elements coming. How would you?
Square root of n slice sets or something.
Square root of n? I think. Pardon? binary grouping. Yeah, good. So all of these are good ideas. So we will go with the binary grouping. So we have 8 elements, let's say. So when the first comes, you let it alone. When 2 comes, that's a binary, it's 1, 0, so you put 1 and 2 together. When 3 comes, you leave 3 alone and 1 and 2 by itself, so you have a cost of 1 at that time, but the second cost is 2 at that time. Then when 4 comes, you unite, you keep going. And it's not hard to prove that the cost of this is theta n log n. You're going to maintain the total of n log n. Each thing is merged at most log n times, so you get theta n log n. And in fact, that's optimal. OK, so this work is about the same problem. So it's a very simple problem. You can keep it in your head, try to solve it. The only difference, the only change to the problem is that now each item has a weight attached to it. Okay? So it's a weighted version of that problem. And we will look at 2 problem variants. And we will follow the paradigm of competitive analysis to solve this. And in general, the items could be inserted, deleted, and the way deletions are done by explorations, updates, deletes. But for this talk, I'm only going to talk about insertions. Okay? And the 2 problem variants I'm going to mention, both of those are open, but we have some results for this. Okay? So I'll stop here. Is the question clear? 2, good. Okay. So the background for the remainder of the talk, I will go over the motivation, describe the problems, just give a sense of some of the results, and close with open problems. Okay, and Kirk will stop me at the right time. Okay. All right, so here is the background. The motivation for this problem came from external memory data management. So imagine we have a static, let's say we have a situation where there is a static data structure. So static data structure basically means you have a single set of items that you have built together originally, and then you organize it in your database, and then you're getting sequence of queries. Now, you could take that and convert it into a dynamic data structure where, and again, I'm ignoring deletions at this point, you're just getting inserts, and periodically you're getting queries, and then you're answering this. That's the process of dynamization. And this idea was originally introduced by Bentley, and then there's a lot of work by Bentley, Sachs, Mellon, and a lot of others. So the idea was, okay, the way we are going to do is as items get inserted, we are going to insert so far in a collection of static data structures. And these are called components. When an insert happens, you build some new components from scratch, you delete some other components. And when you want to do a query, you are going to query all the components that you have built in your database. Okay? And now you'll see the connection to the model. And the whole question is on how to destroy and build components. You're trading off the cost for building versus the cost for querying. Okay, so here is an example. So let's suppose we have 2 components at this point, x1, x2, x3, and x4, and x5. An insert happens, x6. You could choose to do at this point, OK, I'm going to throw in x6 along with x4 and x5. So I'm going to destroy x4, x5, and I'm going to build x4, x5, x6. So destroy and then build. So that's one way to think about it. OK? For our purposes, we won't worry about the cost of destruction, but the cost of build for us would be proportional to how much ever items we are putting in here. So one of the places where this problem appears is in LSM systems. These are so-called log-structured merge systems. So the setup typically is you are doing sort of lots of inserts, and those inserts are actually all cached in RAM. But periodically, you flush those inserts into your disk where you have all these components lying around. So you have a whole bunch of things that you want to put it in disk. So at that point, you have to decide what to do with that whole bunch of things. So you're going to build that component, you want to merge with some others, you want to destroy new components, you can do whatever you want. But in the end, so you pay a cost for building that, and then you pay a cost for querying. When you query, you check the cache. If it's not there in the cache, then you're going to query all of the components because you do not know where these things appear. And the cost of query is just the number of components because there is checking a given component takes just one disk access using some smart in-memory, in RAM disks, indices. Okay? So that's the motivation. Any questions? Yes?
Yeah, so as you draw in the picture, in LSMs, I can have a copy potentially of each item at each level. Does that affect the argument that you made in the beginning?
Good. So what I'm going to describe each item, the copies would be treated as separate things for the purposes of this.
Right, so it's like an item in a version or something.
An item and a timestamp, right. And in fact, that is often how updates and deletes are implemented. So update would simply be you just add another timestamp to it and insert it. A delete actually often would be a tombstone item. So you would put that and put a tombstone. And sometimes you have these things called major compactions where you try to actually compress everything. But here we are not going to go with that. And in fact, in this talk, I'm just going to talk about insertions primarily. All right? OK, so in fact, this problem came from work on Google Big Table, similar kinds of problems, although the compaction techniques vary in sort of level DB and many of these LSM systems that use some version of this. OK. So let me introduce two problems, and then I'll talk about some results for these two problems and close with some more problems. So as you can imagine, at least at some level, the simplest problem you can think of is what we call min-sum dynamization. So the input is a sequence of insertions. Each insertion is a collection of items. Each item has some weight. Okay, so it's a sequence of sets of items. At every point of time, you have to maintain a set cover. A set cover is just a collection of sets that covers all the items. So very clear. What's the input? What's the output? Your cost is at every point of time, you calculate how many sets you created. How many sets you created? What's the cost of building the set? And the cost of building sets is simply the sum of the weights of the items. And then at each point of time, how many sets do you have? Yes.
Where do the weights come from in practice?
Good. So the weights are, so the inserts correspond to sort of size of the thing that is being inserted, and it's actually two things I would say. One is the weights play a significant role. Secondly, actually the weights make the total cost smaller than. So if you were to adopt a strategy that completely ignored weights, that will be much, much worse than if you take into account weights. So in fact, we are trying to be competitive against the best solution with weights. So taking into account that this is a weighted problem saves you a significant amount of cost. Okay, so let's suppose at time 1, input came AB. Let me try this. Okay, so suppose you decided to keep them separately. So you put them, that's your cover. At that point, you incur a query cost of 2. Your build cost is the weight of A plus the weight of B. If at time 2, you got C, you decided to merge that with A, then your query cost remains 2 at that step because you have two things in your set cover. And the cost of weight of A plus weight of C because you put A and C together. Time 3, DE. Let's say you decided to create an entire set out of D and E. Your query cost is 3, and your build cost is weight d plus weight e. And let's suppose at time 4, f came, you decided to merge everything together, you're ending up with a query cost of 1 after that, and then your total weight is this. And the total weight of your algorithm then is simply 8 plus this. Yes?
Another question. So, do you batch together all the arrivals between queries?
Good question. So the question basically is, the way I've described it, essentially every time I'm saying inserts followed by a query because I'm adding the number of sets, yes. But this is without loss of generality. You can mimic you just insert a 0 batch between 2 queries. If you have an insertion, if you're going to flush a cache at some point and then you have a series of queries, then you have another insertion, then just imagine you're inserting empty things between the two. And you can do it anyway. So this is without loss of generality. Okay. Okay. So you could do the algorithm divide. This would be a minimized build cost. And it'll get some bound. I don't think we need to go into the details. But on uniform, it will pay a theta n square cost because it pays the build cost of theta n. You could do unite. This will minimize the query cost, aimed at minimizing query cost, but it'll end up in the uniform input, it'll end up paying this. Of course, on real input with different weights, it might pay anything else. Both of these are suboptimal. The binary transform of Bentley will do the binary thing, ignoring weights. And this is something which is optimal for uniform input, but it's optimal for uniform input, but it is the competitive ratio for something like this problem would be log n. Okay, so it's not the best you can do. So that's the min-sum dynamization problem. The second problem that we look at is exactly the same setup, but now we insist that at any point of time, the number of sets you will maintain is a fixed bound, at most k. Okay? And in fact, this is the problem that actually is of more interest to practitioners. In fact, Google Bigtable has a certain parameter k, and it maintains that number of k. And many, these are called horizontal systems that LSM systems that maintain this category. And actually, this is the problem for which we have certainly more open problems than otherwise. Okay. But otherwise, it's the same thing. So this is the constraint, and you need to have this weight bound. For this, Bentley and Sachs gave a sort of, I don't think you need to parse this, but there is a very interesting scheme which is called the k-binomial transform, and that is the best possible for uniform input, but again, for non-uniform inputs of our kind, it's suboptimal. Okay, so for both of those problems, the setup we have is prior results are for uniform input, but in LSM systems, inputs are non-line and non-uniform. And we are trying to use competitive analysis, which is a very standard framework. No need to give the definition. And our question is, what competitive ratios can online algorithms achieve? Okay. All right. So I will state the results, and I will just give a quick overview of one of those, and then I'll go to open problems, and that's pretty much what the time we have. All right. So our main results are, there is a very nice online algorithm, which is the generalization of Bentley's original binary transform, which has a competitive ratio of theta of log star n. I never imagined that there would be 3 talks in a workshop all having log star n kind of bounds, but yes. So it is it's a tight analysis of that particular algorithm, but it's open whether you can beat this or not. For k component dynamization, for the deterministic algorithms, we get a bound of k, and this is exactly tight. And this one is only for insertions Our results here extend to the case of deletes and updates and so many of those, but not in all the cases. But they allow lazy deletions, updates, item expirations as they occur in big stereo. Okay. So immediate open problems, constant competitive ratio. Can we achieve this? There is no obvious reason we think that cannot be done, but we have no idea how to pursue that. The randomized algorithms for k-component dynamization, which is the problem which is of more interest, is, I think, completely open. I will say a little bit about it at the very end. And trying to handle all the possible extensions for both of these problems is OK. All right. So I'll give you a very, very quick sense of the min-sum dynamization. And then I'll say a little bit more about the k-component dynamization. So how much time? 5 minutes?
Yeah, that sounds about right.
OK. OK. So that's the problem. The algorithm that we propose and we analyze is fairly simple. It is essentially sort of a weighted extension of the binary algorithm. So call it weighted binary. So whenever a new batch comes in, you create a new set out of this batch. And then you look at the largest. So you're looking at time as time goes along. So you look at the largest multiple of 2 to the j that this current time corresponds to. We are going to merge all the sets that already exist whose weight is less than or equal to 2 to the j into one set. Just like in the binary case, except in the binary case it was based on sizes. Here we do it based on weights. Okay, so roughly every 2 to the j time steps, it merges together all sets of weight 2 to the j or less. Okay. So that's the algorithm. Just to show you, I'll show you an example. So imagine we had this sequence of batches that came. Okay, these are the sort of 2 to these are the weights. Think of it as this is a weight 2 to the 9 item that needs to be put together. So there are 2 to the 6 times. So 2 to the 6 different instances of 2 to the 9, followed by 2 to the 5 instances of 2 to the 10, 2 to the 4 instances of 2 to the 11, and so on. Okay, so these are the insert batches above in left to right order. And imagine after that there are lots of queries. So that corresponds to empty batches being inserted. So what will happen is nothing interesting will go on until time 2 to the n minus 1, because remember, the first time we will do any merge would be when looking at things of weight less than or equal to 2 to the 9 at time. Before that time, you will be only looking at things of weight less than 2 to the 8 or less. So nothing interesting goes on until time 2 to the 9 minus 1. At time 2 to the 9, you decide, oh, you're going to merge everything in 2 to the 9, of size 2 to the 9, into 1. So now you have a set of weight 2 to the 15. And you go along at time 2 to the 10, you're going to merge everything of weight 2 to the 15, 2 to the 10, and you get 2 to the 15. Keep going. Okay? And now, at this time, you're going to build these, because at time 2 to the 13, you're going to merge all of those of size 2 to the 13 to form 2 to the 16. And at time 2 to the 14, you're going to merge all of those of size 2 to the 16. Then the next interesting thing will happen is at time 2 to the 15, you will merge all of those to 2 to the 17. At 2 to the 16, you will merge those two, and then that's it. That's the process by which you're building these things. Okay, so that's an example execution. Now, this example execution also illustrates why you actually get a log star and lower bound for what we are doing. Okay, it's difficult to see at this time of the day and at this point of the workshop, but so the desired merge tree sort of greedily in reverse, if you have to build it, this is what we will do, and repeatedly you choose the next node to split and the next unused threshold, and we can show that the number of nodes at depth d is at most a tower of height d. So the optimal thing to do would be, you would be paying log star n merges when the optimal thing would only had to merge once per item. Okay, so I think it'll be, so it's basically the same thing we sort of did in the reverse fashion, and the optimal thing would be to sort of merge all of these at once at the beginning, as opposed to doing repeated merges until the very end. Okay. Okay. So upper bound is much more challenging, and I don't think I'll go into any sort of level detail. We basically query cost, we sort of charge it directly to the build cost, so we just focus on the cost of building. And again, we look at this merge tree, and we argue that the merge tree will have a weighted average leaf depth of order log star n. So it's not necessarily going to be perfectly balanced. It's actually going to be, but their weighted average leaf depth will be order log star n, and that's why the total merge cost will be no more than the number of items times log star n. And since the number of items is a lower bound on the optimal, you'll basically get that bound. Sorry, the weight of the items is a lower bound on the optimal. Okay. I'm not going to be able to go over, I'll just talk about the problem, just remind you of this problem. And the lower bound is fairly sophisticated. I think it's an example, but so I'll skip the lower bound. So this is the k component dynamization where you're limited the number of components. You're bounding the constraint on the number of components. We can show that any deterministic online algorithm has competitive ratio at least k. I think this is too much content here, so I'm going to skip that. But it requires some effort to try to extend it to general K. There are two algorithms that we can give. One is a recursive algorithm, and one is a primal dual algorithm. I think I will go over the primal dual algorithm. It's easier to see. Basically, the idea is you'll maintain some sets. You have k sets in your cover, so you maintain some kind of a credit for every set, and you keep increasing the credit of the sets until one of the sets has the credit to be at least the weight of the set that you're trying to, at least the weight of that particular set. We pick the oldest such set, and then we merge everything that arrived before there. So this is what is called the newest first. So you always try to merge together sets that are sort of the most recent. And then you add the new thing you merge, and then you add it with credit 0, and then we continue. Of course, there's not at all obvious why this works. I think I'll skip the proof, but it's a relatively straightforward primal dual, a greedy dual argument for trying to establish why this works. Okay, let's see. Yeah, so I think I'll just close with open problems. As I said, for the min-sum dynamization, is there a constant competitive algorithm? That's still open. What is the best ratio achievable when you allow expirations, updates, and lazy deletions? I think here we have some ideas about it, although it becomes quite technical, so we don't have any results there. Perhaps the most interesting question is what we can do for the k component dynamization. And I think the question that we have spent a fair amount of time is there a randomized algorithm that beats k? And in fact, there is. Using the primal dual paradigm of Bukwinder and Sefi here, we can show that a k minus epsilon, and I think, and this epsilon is basically for k equals 2, our number is like 1.99998 or something like that. So we can show that in principle it's possible. So you would have thought, because we are struggling, we thought maybe k is a lower bound, but k is not a lower bound. We can actually beat. But there is a lot of interesting characteristics of this problem. And in fact, for people familiar with the classic problems of rent or buy or TCP acknowledgement, many of those questions come up here. But the problem is subtly different, which is why sort of the results don't port. So I think there's a sort of a very nice theoretical work to be done there, although we have some results, but it's very preliminary. From a more practical standpoint, there are a number of questions. The K component algorithm is newest first, but the min-sum dynamization algorithm is not newest first because we merge together things of different sizes, which might be at different ages. But many practical LSM systems want newest first algorithms, so that's a good question. And in general, taking care of all the different kinds of queries is also an open question. Okay.
Sure, last one.
Yes.
Do they use any of these things within Google? Or?
I don't know. The big table, the algorithm does something, at least used to. I don't know the current setup. But the original big table algorithm, which was for the problem of this K compaction, is different. And we can prove that it's not competitive in the same way. I think the motivation was in that context, and there was a lot of, we've also done, I know Neil and others have also done sort of average case analysis, which also suggests some other ideas. I'm not sure how much of those have made into the product.
Just a quick couple comments on the schedule. So, like 10 minutes until the walk. Does that sound about right?
Okay.
All right. So.